This session is about atomic structure, which is in paper 1 and is in combined and triple science. The atom is very small. It has a radius of about 1 × 10⁻⁻10 meters. It has a positively charged nucleus with protons and neutrons surrounded by negatively charged electrons. The radius of a nucleus is about 1/10,000th the radius of an atom, and most of the mass of an atom is concentrated in the nucleus. The electrons are arranged at different distances from the nucleus. The electron arrangement can change if it absorbs electromagnetic radiation, which allows the electron to move further from the nucleus and up an energy level. Or it can emit electromagnetic radiation, and it falls down to a lower energy level and moves closer to the nucleus. We represent atoms with an atomic number and a mass number. The atomic number says the number of protons, and a particular element will always have the same number of protons. For example, carbon always has 6 protons. The mass number is the number of protons and neutrons. There's an example here of cobalt. Now you don't need to remember the actual symbols for the elements, but look at the atomic number on the bottom. This is 27 and gives us the number of protons, whereas the mass number at the top, 59, is the protons and neutrons. So if we're working out the number of protons, we just look at the atomic number, 27. But to find the number of neutrons, we need to get the mass number and subtract the atomic number. 59 minus 27 gives us 32 neutrons. Isotopes have the same number of protons but a different number of neutrons. This is an example of lithium. It always has 3 protons, so the atomic number will always be 3. But the first one on the left has 6 protons and neutrons. This means it has 3 neutrons. The one in the middle has 4 neutrons, and the one on the right-hand side has 5 neutrons. There were different models of the atom, and when we get new experimental evidence, we need to update or change our model. But before the discovery of the electron, atoms were thought to be tiny spheres that could not be divided at all. But once they discovered the electron, they came up with the plum pudding model of the atom. This is a ball of positively charged with negative electrons embedded in it. It doesn't have a nucleus or any neutrons. Then they did the scattering experiment, where they fired alpha particles at gold foil, and this suggested that the mass of an atom was concentrated at the centre and the nucleus was positively charged. This new evidence meant that they had to change the atomic model, as it contained protons and neutrons with most of the mass of the atom at the centre of the atom. So the nuclear model replaced the plum pudding model. It had a very small nucleus with most of the mass, and the electrons are in shells around the nucleus. Bohr and Chadwick continued their work on the atom. Bohr adapted the nuclear model and suggested the electrons orbit the nucleus at specific distances. And then later experiments discovered that the positive charge actually came in smaller particles, which they called protons. James Chadwick, about 20 years later, provided evidence to show the existence of neutrons. Some atomic nuclei are unstable, and they throw out radiation to become more stable, and this random process is called radioactive decay. There's a difference between activity and count rate. Activity is the rate at which the source of the unstable nuclei decays, and it's measured in becquerel. But radioactive materials give out radioactivity in all directions. If you have a Geiger-Müller tube recording it, it can only record the radioactivity going in one direction towards it. So the count rate is the number of decays recorded each second by a detector. The first type of radioactive decay to look at is alpha decay. This is made up of 2 neutrons and 2 protons, which is exactly the same as the helium nucleus, the helium atom without the electrons around it. Alpha particles are the most ionizing because they have a 2+ charge, but the least penetrating because they're big and heavy, so they're stopped by paper and skin. They're represented by the symbol 42He, and you need to learn this symbol. An example of alpha decay is radon decaying to polonium. Look at the numbers on the top. The numbers before the arrow have to equal the numbers after the arrow. So 219 equals 215 plus 4. And the same for the numbers on the bottom. 86 has to equal 84 plus 2. The part you have to learn is the 42He. The rest you can work out. A beta particle is a high-speed electron which is thrown out from the nucleus when a neutron changes into a proton and an electron, and the electron is thrown out. Beta is stopped by thin aluminium, and it's represented by the symbol 0 minus 1e, as it's an electron. An example of beta decay is carbon decaying to nitrogen. Again, look at the numbers on the top. 14 equals 14 plus 0, and on the bottom, 6 equals 7 minus 1. Gamma radiation is an electromagnetic wave that's emitted from the nucleus, so it doesn't have any mass or charge, and it doesn't change the nucleus, so it doesn't need an equation. Another type of unusual decay is a neutron. Neutrons can sometimes be emitted by radioactive substances after a collision with an alpha particle, which causes the nucleus to become unstable. Radioactive decay is a random process, but if we have large enough numbers, we can use some statistics, and we define the half-life as the time it takes for the number of nuclei of the isotope in a sample to halve, or the time it takes for the count rate to fall to half its original level. We can work out the half-life from graphs. In this case, the initial count rate was 600, and to find the half-life, we halve this, which is 300, and draw a line across and down on our graph, and we can read off the time of the half-life. Make sure you check the units on the x-axis. This one's in minutes, so the half-life will be 45 minutes. Contamination and radiation are quite different. Contamination is the presence of radioactive materials which have been mixed up with the sample. One of the problems from this is that that radioactive material will continue to decay until you've got it out of the object. Radiation is slightly different. Irradiation is exposing an object to nuclear radiation, but it doesn't become radioactive itself. So which of the strawberries would you rather eat? The ones that have been irradiated with gamma radiation, or the ones that were contaminated with radioactive rain after a nuclear disaster?